Polar bond cleavage is a lot more common in organic chemistry than homolytic cleavage. This is where the electrons in a bond basically move onto one atom or move from an atom to another, and they move as a pair. So this is what we've already encountered, a full arrow showing a pair of electrons moving from one place to another. In this example, you have two atoms. There's other atoms that can be attached to them, but two atoms, and there's two electrons in the bond between them. When you have that full arrow moving onto one atom, what we're showing is both of those electrons have to move onto this atom, and they become a non-bonding pair. Before, you have two electrons being shared by two atoms. Now, both of those electrons, which was a net 1 formally on this atom A, both of those electrons move away. So now A is left with a net positive charge. And because only net 1 electron was on boron when it was being shared, and now both of them are on the, not boron, but the atom B, it's not boron. Now they're both on B. Now the net charge on B is negative. Likewise, when electrons move from a non-bonding pair to become a bond, now a positive charge is gaining electrons, so it becomes neutral, and something's negative is losing electrons. In every single one of these examples, when you're looking at drawing your arrows, first think, what's happening to those electrons? Are those electrons, where are they moving? And think it through that way. Don't think movement of the atoms, think movement of the electrons. Then think, how must charge be changing? If electrons are moving away from an atom, it must be becoming more positive. If it's negative, it becomes neutral. If it's neutral, it becomes positive. If electrons are coming toward an atom to form a bond, then you think, well, if it's gaining electrons, it has to become more negative. So if it's positive and it gains electrons, it becomes neutral. If it's neutral and it gains electrons, it becomes negative. Always think through each thing very analytically. Okay, and this is just going over it again. Electrons are leaving A, so it becomes more positive. Electrons are coming onto B, so it becomes more negative. Electrons are going to A, so it becomes more negative. Electrons are moving away from B negative, so it becomes more positive. Okay, so now what we're going to do is look at the deprotonation of water very slowly and carefully and see what happens with the breaking of the bonds and the electrons. What we're going to do is we're going to break this bond. Now, this reaction doesn't really occur unless you're in the gaseous stage. It can occur. But in water, this never happens. The hydrogen just doesn't break away from a water molecule. A proton doesn't break away from a water molecule. It would be in water that another water molecule would pick up a proton. But we're doing this just to show the demonstration of how you would show a bond breaking. So what actually happens here? You can see the hydrogen becomes a proton, so it's more positive. The oxygen's becoming negative. So you ask yourself, which way are the electrons flowing? The electrons are going away from the bond and onto the oxygen, or out of the bond and going onto the oxygen as a non-bonding pair. So the oxygen's going to get a negative charge because the electrons are moving, because the hydrogen's getting a positive charge, the electrons must be moving away from it. And so they're going onto the oxygen. Okay? We show it with an arrow, and so we show the flow of electrons. Electrons going from the bond onto the oxygen. Okay, now we're going to look at the protonation of an alcohol. Now it's the formation of a bond. So what happens in this reaction? These electrons reach out and grab the proton. Notice that forms a bond right here, because the oxygen is now having its electrons leave it, it gets a positive charge. It's not leaving it completely, but full electrons going into a bond is going from 2 electrons to 1 net electron formal charge-wise. So it becomes a positive charge on the oxygen. The hydrogen was positive, electrons are reaching out to it, so now it becomes neutral. So basically the non-bonding pair becomes the bond right here between the two. And we show an arrow showing that bond formation. Draw in the arrow to show protonation of water. Some of you may be saying, we're doing this all over again. But the reason I'm doing this again is that the first time we did this on the first exam, not everyone gets this. So it's really important that you understand how to do these mechanisms because they're going to be an integral part of this course. And without understanding mechanisms, organic chemistry becomes way too hard. So if you got this already, you can fly through this part of the online lecture. If you didn't, go carefully through this slowly to try and understand how to do arrows and mechanisms. Okay, now to show the protonation of water, what actually happens is the non-bonding pairs here are going to reach out and grab that proton. So let's show it with an arrow. There we go. And that's all that's needed. Now, on this, go ahead and show how hydroxide will remove a proton from an ammonia molecule. Okay, to do this, the hydroxide is going to reach out and grab a proton. To do that, it must have an arrow to do that. So here, it takes its non-bonding pairs and reaches out and grabs a proton. Do not show an arrow going from the hydrogen over to the oxygen because we are not showing atom movement, we're showing electron movement. Now, hydrogen cannot have 2 bonds. So what must happen is this bond here must break. So to break that bond, we show that with an arrow moving the electrons from the bond onto the non-bonding pair of the nitrogen. Notice how charge changes. Oxygen was negative, it reached out with its electrons, so it became neutral. The nitrogen was positive, but electrons jumped onto it to form a non-bonding pair, so now it's neutral. Here is the protonation of an amine. All that happens is the non-bonding pair reaches out and grabs a proton. Notice the nitrogen basically goes from having 2 electrons on it alone having net 1 electron on it in a bond. So it becomes more positive. The hydrogen went from having no electrons to having net 1 electron sharing. 2 electrons give us net 1 electron being added to it, so it becomes neutral. To show the dissociation of an acid, which again does not occur in water, this can occur in gaseous stage, but it doesn't occur in water. The water would pick up the proton from it. But again, we're just showing bond breakage. The electrons go from the bond onto the oxygen, so now it becomes negative. Important points. If an arrow goes away from an atom, it's showing electrons leaving, so the atom becomes more positive. If an arrow is coming to an atom, that shows electrons coming, so it becomes more negative. If you have electrons come in on one side and leave on the other side, there's a net no change of electrons, and so there's no change in the charge on that atom. Remember, if you have a bond split by 2 half arrows, there's no charge. You have free radicals developing. So remember, charge is always conserved. If the sum of charge on one side is negative, the sum of charge on the other side must be negative. If the sum of charge on the left is positive, the sum of charge on the right must be positive. If the sum of charges on the right is neutral, must be neutral on the on the left. Check that always to make sure that you didn't make any mistakes. So now you're going to try some problems. Go ahead and figure out what is the mechanism for the protonation of T-butanol with the hydronium ion. So go ahead and draw the hydronium ion and draw in what arrows you need to show for the protonation of T-butanol with the hydronium ion. Okay, so first thing we have to do is draw in the hydronium ion. Okay, there's the hydronium ion. Now to protonate T-butanol, it's basically going to be a proton transfer from the hydronium ion to the T-butanol. Okay, what's going to happen is the electrons on the oxygen are going to reach out and grab a proton off the hydronium ion. And that's how you would show it with the arrow. Now, notice this hydrogen cannot have two bonds. This arrow is showing electrons forming a bond with this. So now this must lose a bond because hydrogen can have only one bond. So the electrons are going to move somewhere from this bond. Where do they move? They move onto the oxygen. The product of this will be this plus another a water molecule not shown. All right, and you see here is a bond that just formed. Notice the oxygen becomes positive. Why? Electrons left it. And if we had the water molecule over here, you would see it was neutral. Why? Electrons went from the bond onto the oxygen and neutralized that positive charge. Go ahead and try to figure out what is the mechanism for hydroxide removing a proton from the protonated isopropanol right here. All right, this is the protonated compound, which is going to lose a proton. What's going to remove it? Hydroxide. Now, we draw a hydroxide oftentimes as OH negative, but where is that negative residing? On the oxygen, not on the hydrogen. Where is it in? Non-bonding pairs that are not shown. So what's going to happen is that oxygen is going to reach out with a non-bonding pair and grab a hydrogen. Here's an arrow to show that. Now, what must happen, because the hydrogen cannot have two bonds, being bound to the oxygen, and this oxygen can't happen, so the electrons in this bond must jump onto the oxygen here. Notice, this oxygen's gaining electrons, so that positive will become neutral. This oxygen is losing electrons, so this oxygen becomes neutral. And the net reaction is, here we go. There's isopropanol with the proton gone and neutral charge, and there's water as the product of the reaction. Notice there is charge conservation. The sum of charges over here is neutral. The sum of charges over here is neutral. We can show just plain bond breakage. Here, electrons are jumping out of the bond and onto the oxygen. Notice we get a positive charge on the carbon. This is a positive species. Overall, we have positive over here. What happens? Electrons left the carbon-oxygen bond onto the oxygen, which had been positive, so now it's neutral. The carbon lost electrons, so now it's positive. Here, a bond is being formed. What's happening? Electrons that are in a non-bonding pair, or you can say the negative charge, is reaching out to form a bond with this carbon. Because electrons are going away from the negative charge, you get a neutral on the bromine. Because electrons are going to the positive charge, that positive now becomes neutral, and a bond forms. Go ahead and draw in the arrows for this reaction. Well, if I look at this, I can see that this carbon becomes attached here. So I'm going to show, you can either show the negative charge or the non-bonding pair, it doesn't matter. It is going to reach out and form a bond with this carbon. Well, this carbon, if it gets a bond here, is going to have 1, 2, 3, 4, 5 bonds. Can't happen. So one of these bonds has to break. So let's take one of the double bonds. The pi bond is weaker than any of the other bonds. So what does it do? It jumps onto the oxygen to form the negative charge. Go ahead and draw in the arrows for this reaction to occur, and then restart the lecture. Okay, you can see that this hydrogen is going to end up on the oxygen there. The temptation for students is always to draw an arrow showing the hydrogen moves here. But remember, we're not showing movement of atoms, but we're showing movement of the electrons. So we have to show electrons moving out to reach out to the hydrogen to form a bond with it. There are two ways of doing it. One way is to have a non-bonding pair reach out and grab the hydrogen, and then for the electrons that are here in this bond to move onto the oxygen to form another non-bonding pair. And then because the hydrogen would have two bonds, and it can't have two bonds, the electrons in this bond have to move onto the chlorine. The other way to do this would be to show the electrons that are in this pi bond instead hinging over, bink, to the a bond between the oxygen and hydrogen, and that would replace this step and this step. You can do it either way. Go ahead and draw in the arrows for this reaction. Okay, if we look at what's happening is one of these hydrogens actually becomes attached to this carbon, and this bond breaks homolytically. You notice that this magnesium becomes positively charged. So what must that mean about these electrons here? These electrons must be leaving the magnesium. So we can draw an arrow to show them leaving the magnesium, and what do? They reach out and grab this hydrogen. Well, hydrogen can't have two bonds. Notice there's a negative charge on this oxygen. These electrons here must be ending up on the oxygen. All right, those are some reactions that we've tried, and now you need to try more problems in the book, because unless you practice this, it doesn't get set into your head. So make sure you do lots of book problems, as many as you possibly can, and I might provide some more for you with some problem sets.